This is Lesson 6, Exercise 7F, using least squares line to model a linear association. The learning goal is to know what a least squares line is, where it comes from, the workings of residuals, and the arithmetic method of working out the least squares line. The success criteria is to work out the equation of a least squares regression line by hand and using the ClassPad calculator. Once we identify a linear association between two numerical variables, we can go one step further by fitting a linear model to the data and find its equation. This model gives us a better understanding of the nature of the relationship between the two variables. We can also use the model to make predictions based on this linear model. Now, these predictions that are made are heavily relying on some type of line, an equation, and this equation is what we'll be looking at and how to create this equation. The process of modeling an association with a straight line is known as linear regression, and the resulting line is often called the regression line. In Chapter 6, Linear Models and Graphs, you learn to fit a linear model to a scatter plot by eye. This method is somewhat problematic because everyone will get a different answer. A better approach is to fit the line according to an appropriate mathematical strategy known as the least squares method. The theory behind it goes like this. When fitting a line to a scatter plot, we are trying to find the best fit, as we know scatter plots rarely lie exactly in a straight line. There will always be errors. In other words, when you put this line in, for this example here, when this line goes directly as a best fit in the middle of these data points, you can see that there's this little distance here that each scatter point is away from the line. And this right here, these errors or predictions are called residuals. Now, residuals are the vertical distances from each data point. To find the best fit, you need to minimize the residuals. Residuals are an important part of further mathematics and can help you decide if data is linear or nonlinear. When we see here, when these residuals are minimized, i.e. the distance away these points are from the line gets lower, it's safe to assume that the R value, the Pearson's correlation coefficient, will get closer to 1 because they're getting closer to this line. But the further away these points are, the more the distance away is, the higher the error or the residuals, meaning that the correlation coefficient of R will be tending towards 0. So the practice behind the least squares regression line is that the assumptions made in using the least squares method to model a linear association are the same as those for Pearson's correlation coefficient. And to remind you what these three assumptions are, the variables both need to be numerical, the association needs to be linear, and again, there are no outliers. Besides fitting a line by eye, which is not very accurate, there are two other ways to find the equation of the line. The arithmetic method, used when summary data is given, and we'll look into this in the example, or using a ClassPad calculator when the raw data has been provided. So you're going to use two methods. When summary data has been provided and given to you, you will use this arithmetic method. But when raw data has been given to you, when you only got data points, then you have to use your ClassPad calculator. Here we will look at the example of how to use the arithmetic method. The equation of the least squares regression line is given by y equals a plus bx. When we worked on Chapter 6, we knew that we had to find a value for a and we had to find a value for b. How to find these values is given by these two formulas here. The slope also known as b, is given by this equation r times s subscript y divided by s subscript x. Now this right here, the sy and the sx, would seem very new to you. The R value, which is Pearson's correlation coefficient, hopefully by now you should have some understanding of this. Now how this is worked out, we're not going to look into. Sy and Sx is what's called the standard deviation. So S just stands for the standard deviation. And we don't really look into standard deviation while we're doing general maths in year 11. But to put it into a nutshell, standard deviation just talks about the average spread of the data values within that data set. So for instance, if I had a data set that looked like this, 1, 2, 3, 4, 5, and then I had a data set that looked like this, 2.8, 2.9, 3, 3.1, 3.2. Both of these data sets have 5 values. Both of these data sets also have a median of 3. But as you can see here, the spread of these values here in comparison to these values here is greater, because this is going up by 1 unit on average, where this is going up by 0.1 unit on average. So when someone says, hey, what's the median of this set of data, and you said 3, and you said, what's the median of this set of data, and you said 3, while the median does hold its importance, there's still not enough information to talk about what the spread within these values are. And so we use a formula which, when worked out, will give you the standard deviation. And deviation just means to deviate, to stray away from something. And we're trying to find the closest value for this. So we know that this deviates away from the middle by an average of 1 unit, as opposed to this, which deviates an average of 0.1 units. And that's all standard deviation means. We're just seeing the average spread within the data values. So whenever we look at S of y, all we're doing is just getting the standard deviation of all the y values. And then standard deviation of x, or S subscript x, again, standard deviation of x. Very tricky to show you without context, okay? But all you got to know is the standard deviation just means spread. And what you do with this is you get the standard deviation of y and multiply by r, and then divide it by the standard deviation of x. The intercept, or the a value in this case, is given by y with a little line on top, which we know as, or we call it as y bar, minus b times x bar. And y bar and x bar, shown by this point here, are just the mean values of x and y, or the common average for x and y. So right now you're seeing these two random equations where there's a lot of proof and mathematical proof behind why these works. But at the end of the day, all you have to know is you're finding an equation and you're getting an a value and a b value. In previous exercises, all we had to do was just get 2 points, and you can get your slope, and you can also get your y-intercept, which is really, really simple. But now we've got all these random points within a scatter plot that are given, so more work has to go into it. Let's look at this example here, where we're going to find the least squares regression equation to 2 significant figures. And in this case here, we've got our average for our x values. So data was given, and we worked out the average, we added them all up and divided by however many data points there are, and we end up getting 5.6. And we got the standard deviation, which is 1.2. So where on average, we know that the units stray away on average by 1.2 units from X bar, or you can do it from the median. Y bar, or the average for Y, is 110.4, and the standard deviation is 5.7. So it strays away, each data point strays away from the middle, an average of 5.7 units. And our Pearson's correlation coefficient is 0.7. So it's a moderately strong connection that we have within here. Now, there's no context behind this. We don't know what the data is about. And this is what it means by summary data. We've given a summary of all of our data here. And so when we get this, we just use these two equations to work out our least squares regression line. All it is a straightforward substitution. We first want to get our B value because we have to rely on B here. So you can't work out your A first without working out your B. And the B value is just R times S of Y divided by S of X. Our R value is 0.7. We're multiplying this by S of Y, so the standard deviation of Y, which is 5.7. And we're dividing this by a standard deviation of X, which is 1.2. Again, you're not meant to know how this formula works. Okay, we're not going behind the scenes. We just know we're finding a B value. We're finding a slope. How steep is this slope? This ends up being 3.325. Now the question saying that it has to be to two significant figures. So this will be 3, there's our first significant figure. And then our second significant figure, which is also 3, we've got to see if this 3 stays the same or rounds up to a 4. In this case, it stays the same because the value afterwards is less than 5. So in this case, it's a 2. So our B value is 3.3. So our slope in this case goes up on average by 3.3 given the summary statistics here. Now that we've got our B value, we can now use this B value to obtain our A value. So our A value is equal to Y bar minus the B, which we just worked out, times X bar. This will be equal to our Y bar, which is 110.4, minus, now in this case when we use B, we don't have to use this value here. We can just use the already two significant figured value, which is 3.3, and we're multiplying this by X bar, which is 5.6. Yeah, this ends up being 91.92. We've got to round this to two significant figures. Our two figures are already here, so this will be 9. Now let's look at this one. Let's look at the value after the one, which is higher than 5. So it's 92. So 91.92 is just closer to 92 as opposed to 91. And there's our two significant figures. Now we found our B value and we found our A value. The next thing we want to do, and the last thing we want to do, is get the formula of Y equals, in this case, our A value is 92. And our B value is 3.3. So it's 92 plus 3.3x. And that is the least squares regression line by the arithmetic method. So this line right here, we've now got a straightforward equation that we can put in the middle of our scatter plot. Even though we don't have a scatter plot here, we've got the summary of that scatter plot. We've got a line here we can put straight into the middle. The next and final example is going to be looking at how to do this using your calculator if only raw data has been provided to you. So in this example here, we're extracting information which we did from the previous example, where we looked at 11 countries, their emissions of carbon dioxide given in tons, and the income per capita given in thousands with the context of dollars. So we've already got, hopefully from the previous example, it should be still within my graph here. Yep. These are all the same. I've already listed this down. And the three questions that we have to do is we're going to determine the graph of the equation of the least squares regression line that will enable CO2 emissions to be dicted from income. And this question right here is the reason why we look into our least regression line, because we have been given information right here. And then from this information, we can put a line in, and a proper line, because the maths behind it will be correct. And then with that equation, we can then make a prediction of if a country can provide us, the amount of income per capita that they produce, we can predict their CO2 emissions based on these 11 countries here. Okay, remember, it's just a prediction. It is just a prediction, but it's the very, very accurate prediction as well. So that will be question A. Question B will be writing the equation down in terms of the variable income and CO2 with the coefficients given correct to three significant figures. So in other words, this, instead of writing it as y equals a plus bx, we find out what our a is and what our b is through the calculator, but we have to write y and x as income and CO2, and which one you write down we'll look into once we get into the example. And we're going to determine and write down the value of the correlation coefficient r to three significant figures. Now this can be completed because we did this in the previous exercise, but it's a and b that we're going to work on. So once you have the statistics tab open, so remember menu and statistics here, you're going to make sure that the income in list 1 goes in here and the CO2 levels go into list 2, making sure that both of them hit exactly 11. The next thing you want to do is you want to set the stat graphs. Okay, so we're going to click on this button here, and it's going to ask you what type of statistics graph do you want to plot. Remember, we were used to using the histogram or the box and whisker plot or box plots. In this case, by default, it leaves it as scatter, and that's all we want to do. We want to leave it as scatter. I'm going to press on set, making sure that it's on list 1, list 2, and let's set that. Okay, so now we've just set it. We haven't established anything. We now want to see what this looks like by clicking on this button here to see that graph. And that will show you the different scatter plots. Now mine has already put the line in. Yours might do that, or it might just have it as the scatter plots. Regardless of if it has it in there or not, you can see that there is this positive trend that's going up from left to right. So we actually want to know, what is this equation? How do we get this equation using the calculator? Well, all you have to do, and it's relying back on the previous exercise, you want to go into, you're going to click back onto this table here, and you're going to get the option again, calc, regression, linear regression. Choose list 1 and list 2, press OK, and here we can see our A and our B value provided to us. We already know what our R value is from the previous exercise, which is 0.818. But now we've got our A value and our B value. It automatically works this out. We don't need to work this out by hand. And this is just showing us our A value, which is the y-intercept, and our B value, which gives us our slope. How much does this go up by from left to right? So when you write this down, you've got to make sure that you're obeying the significant figures that is required for this. So first, determine the graph, determine and graph the equation of the least squares regression line that will enable CO2 emissions to be predicted. If you previously just had a scatter plot without that line and then you press OK, the line will then pop up. So I've already done this, so it remembers that I've put it in and remembers that I jotted a line, so that's probably why it's put that in. But if you press OK, the line will go in. So that's A done. B will then say, write the equation in terms of the variable income and CO2 level. So remember, one of this is the explanatory variable and one is the response variable. So one is going to explain the other. In this case here, income, the amount that the country's income is, this will explain what the CO2 levels are. So we have to make sure that instead of writing y equals a plus bx, we have to write that the CO2 levels is equal to, and this is where your a and b values come into play. So I'll get the a and b values back again. Our a value to 3 significant places is 1.3, and because that 8 there might stay the same or change, in this case it changes because the next value is greater than 5. So this is 1.39, and that's where the 1.39 comes from. Our b value to 3 significant figures, remember that 0 is insignificant. If it starts with a 0 point, that value is insignificant. So we count the 4 as our first significant figure. 4, 1. Now this 6 can either stay the same or change dependent on the next value. In this case, it changes and it goes up by 1 unit because this value is equal to 5. If it's equal or greater to 5, the previous number goes up by 1 unit. So our b value is 0.417, and then this will be multiplied by our income. So instead of writing of y equals a plus bx, we're going to write CO2 is equal to 1.39 plus 0.417 times the income. And lastly, it's asking for the r value, which again is just 0.818. Now, there's a lot of information to take this in, okay? A lot of information, sorry, to take in. I can admit that, because we've been given these 2 new equations that seem kind of arbitrary, out of the blue. We haven't really looked into standard deviation before. And there's all these new variables, A and B and R's. All we are doing at the end of the day, if we want to put a little snapshot of what's going on, we've been given data, and with this data, we're predicting an equation for a line. And then with that line, we can make predictions of, depending on what the context is, we can make predictions using that line. This line is the closest thing that we can get to for a prediction, okay? Because you can just look at a scatter plot and be like, oh, yeah, it's safe to say that the taller you are, the more you're going to weigh. Well, now we're getting into the specifics of it. If I was exactly this tall, how much will I actually weigh? I want a unit. And this is what this exercise looks into, okay? So nearly 25-minute video, a lot to take in, but hopefully you guys should get the hang of this, okay? That concludes lesson 6, exercise 7F. 7F, again, just like 7E, you're doing questions 1 to 5, all on the calculator. If the question requires you to show something on the calculator, again, take a picture of it and upload it onto the relevant exercise, which is 7F. See you guys in the next video.